coming here. And I want to thank the QueensJS organizer for hosting such a wonderful meetup for all of us. Yeah, give a round of applause. Tonight I'm going to talk about SpaceCraft. And what is SpaceCraft? SpaceCraft is an open source real-time collaborator which me and my team built, and basically allows users to write and execute Ruby, JavaScript, and Python code directly in the browser. We built this with Node.js, WebSockets, and Docker. And basically what it does is encourage pair programming with no setup required. So before we move on in all the technical details of how I built this, let me just show you guys a demo. So just to give you guys an idea of what it's about. So right now I have two browser sessions open up, I'm going to just type code in it and then show you kind of how this works. So we have, right now I'm in Ruby, I can write some code here on the REPL, and as you can see, it synchronizes in real time. And if I execute this, the output is also synchronized. Now I can also change languages. Oops. So if I change to JavaScript, and let's say I have a function declaration here, and just a simple function, just do like console log, hello plus whatever that's being input. If I run this, it runs in REPL, and I can call this function like this. So this is a basic general idea of what I built so far. Now let's go into the details. Right here. Okay. So to give you an introduction, collaborative programming environments such as what we built here is effective for remote technical interviews because it removes any setup necessary to set up a pair programming environment. So I'm gonna give you guys an idea of what kind of solutions are out there in the market right now. However, those solutions are closed source and they often require user authentication. So the two main solutions out there is, first of all, REPL. So REPL is an IDE that has a REPL and a code editor, and the user can do a bunch of things with it. Can spin up a server even. And they recently announced multiplayer feature, which is a collaborative feature. Right after we finish our project, which makes us really happy because it validates our use case. Next, we have CoderPad.io, which is an interview platform with a code editor and also REPL. However, these two requires user authentication, and CoderPad actually requires paying an account to be able to use it. So why build SpaceCraft, right? We want to build it as an open source alternative, which means that developers can spin up their own REPL and deploy on their own. We also built this because we found that we can solve interesting engineering challenges, and we want to find out how we can scale this further. So, of course, it comes with a lot of challenges. The main challenge is that we first have to isolate user sessions from one another, and also since we are allowing users to enter code into our system, we want to prevent malicious code from affecting that. And lastly, we want to achieve real-time collaboration and synchronization. So I'm going to go into a little bit about how we solve these problems. First, I'm going to go into network architecture. So here are the requirements. We want it to be scalable, which means we want you to be able to handle multiple runtimes, like Ruby, JavaScript, and Python, and so on and so forth. Next, we want to support multiple users per session, and we want to detect when to free up resources when all the client disconnects. And finally, we want to be able to have the server stream the data directly to the client. So we employ a client-server architecture because we don't want to deal with the peer-to-peer nature of all the complexity, and it fits our use case. Now, with that, we want to figure out where should we execute the code, right? You might think that, oh, it can do it in a browser, like JavaScript, right? Easy. However, we found out that we saw this interview from Winston, founder of CoderPad. He says, one day I something up, and I just realized that there was no way I could scale this completely as far as I needed to. What are you going to do? Compile every programming language into JavaScript? Good luck with that. With this, we decided to put all runtimes in the server because that's easier to manage. And also, it's a very scalable solution because we can control how much memory and CPU that we need rather than have the browser decide. The only trade-off is that with that comes with more responsibility. We have to spend money on server resources and potentially more costly. So we started our project with HTTP. It works well with a single request and receiving a single response. However, we can't really broadcast that to multiple clients with the synchronization feature that we want to build. So we opted for WebSockets because it provides a full duplex persistent connection. And why WebSockets, right? WebSockets provide a lower payload of 2 to 10 bytes of additional payload for every request and response, instead of having 200 bytes of header payload for each HTTP request and response. Now, with WebSockets, we can also have a large number of persistent connections. We're looking at about 1,024 connections, and that's plenty. Instead of having 6 for HTTP, that's very limited. Finally, we want to be able to easily detect client disconnection by sending out heartbeats. With HTTP, it's harder to do so, and it's also costing a lot of bandwidth. So now with our network architecture figured out, we want to build the core component of our application, which is the REPL, right? Before moving to how we build that, I just want to give you guys a basic idea on how this works in your local machine. So for example, you spin up IRB, Node.js, or a Python console in your terminal. What it does is actually spins up a REPL shell program at the back end, and the terminal actually performs all the reads and writes with that. And whatever that's being evaluated will be returned to the terminal and displayed to the user. However, what we're building is much more complicated than this because we're allowing the user to interact with REPL program remotely. So we need to figure out how we can manage that communication. And first of all, we figure out that, oh, very easy. We just have our application, Node.js, spin out a REPL program, and write to the standard input, read from standard output, right? Simple. However, there are problems with this because the input and output streams are blocked sometimes, and it's due to maybe some low-level implementation. I won't go into detail how or why that happens, but we just need to know that when that happens, we will have hanging outputs. Now, although there are techniques to unblock those streams and get the output that we want, the techniques differ from different languages, which means that for each language that we add, the complexity increases because we have to write code to handle each one of those cases. The solution is to use Pseudo-terminal. So for those of you who are not familiar with Pseudo-terminal, it's basically just a program that sits between our application and the underlying program and processes all the inputs and outputs so that we can persuade the REPL program that the input is actually coming from the terminal. Now, common use cases are the terminal app actually has a Pseudo-terminal at the backend and connects to the shell program. Also with SSH, since you're allowing the user to interact remotely, you would need to have a Pseudo-terminal as well. So back to our diagram here, the solution is to use Pseudo-terminal. And the advantage, it's very obvious, is that we can offload all the burden of managing input and output streams. We don't have to worry about that at all. And therefore increases the extensibility, which means that when we add more languages, the procedure is the same. We just use Pseudo-terminal, right? And Pseudo-terminal also allows to send like control sequences such as control C, and therefore it will be translated to a interrupt signal to our REPL program, and also can capture full outputs such as colors. The only trade-off is that additional layer of processing, but with all these benefits mentioned, I think it's worth a shot. So with that, our REPL in place, we want to figure out how we can synchronize that between multiple users, right? So I'm going to give you a simple illustration of how this works. First of all, we have our client. Client, let's say, sends out a line of code to be evaluated, and our app server sends it to the Pseudo-terminal, right? Pseudo-terminal sends it to REPL, REPL evaluates it, returns the output, and our app server just broadcasts all the clients, and then output the stream. For input synchronization, it's also very similar. First, for example, we want the client to enter the key open square brackets, right? There's one additional piece of information here we need to track, which is the current state of line. And whenever there's any change in the current state of line, we'll broadcast that to the app server so that we can, again, broadcast to other clients. Then we can update, finally say, okay, all the other clients update their state to have this state that's recently updated, and we can explain the UI. With input and output synchronization, of course, we need to handle conflicts, because what if two users decide to type at the same time, right? What happens, right? So for REPL terminal, it's very easy. What we did is we just rely on eventual consistency. So last write wins. Whoever types the last, or if two users type at the same time, the one that has longer latency wins the update. For the text editor, however, we are expecting users to type at the same time. We don't want to have context drop. We don't want users to, overwrite each other. So we use YJS, which is a shared editing framework that uses CRDT to help resolve that. Now for the container architecture, so right now we have synchronization in place, right? For the container architecture, why we should use container, right? So first of all, remember that we are letting users enter whatever they want into our system. This means that if they happen to have root access, they can override our host system and compromise it, right? So, and there's also another concern that a spike in the memory or CPU in one single session, it will compromise all of the other sessions because it consumes all of the memory available in our host system. And therefore we chose Docker to help us with that. Now, to illustrate how this works is that if, let's say, one application instance is being compromised, we still have other instances unaffected. And if we have one application instance have resource spike, we limit that resource spike, and let's say like 50 megabytes, and only 50 megabytes can be allocated to the application at max. So our current architecture looks like this, right? We have containerized application that makes system calls directly to host kernel. However, there's a problem with this because system calls are made in privilege mode. So we want to prevent that, right? First of all, is to, of course, enable non-root access when the user connects to the container. Next is to use the container runtime sandbox. We actually use gvisor, which is an open source project created by Google that acts as a guest kernel. And what basically does is that intercepts application system calls to make sure that they are unprivileged. So now our architecture looks like this. Much more secure, we have gvisor sitting in between, guarding system calls, making sure that they're all non-root before reaching a host. With a container architecture in place, we want to figure out a way to connect our users to the containers. We use a reverse proxy because we can abstract with all the connections, and also we can add a session ID every time a user requests a new session. That way, any user, other user, won't be able to guess what session they can access other than what they themselves do. So a little diagram to show you a general idea how this works is that, let's say we have 3 sessions here, right? Each URL basically maps to a container IP address. And then reverse proxy basically just forwards that request to the destination container based on the session ID in the URL. The URL looks something like this. We have however many digits of random generated number, and each one of them maps to a specific container IP and port number internally. And that won't be exposed to the user, by the way. With all of that, finally, we want to figure out how we manage multiple sessions. We use Docker Engine API. So within our Node.js, we use a Docker API to interact directly with Docker. So we can start new containers within a new session. We can forward request to a perfect container, and once the session is ended, we want to destroy a container. And this is just a basic diagram. Let's say a client requests our app. Our reverse proxy says, okay, I'll generate a new session ID and create a new URL. And I'm going to start a new container. And then container says, okay, my IP address is this one. So then the reverse proxy says, okay, I'll take this URL and map it to this container IP. Finally, the reverse proxy says, I'm going to redirect you, the client, to the new URL. And from then on, the client can basically be forwarded directly to the container. So So that's all I have today. You can find out more on the website. We have a demo there. We have written a in-depth case study. You can read about it. So thank you. Feel free to email me. I'm currently open to full-time opportunities, so if you feel like I'm a great fit for your team, feel free to reach out to me later after the talk. Thank you.
Woo! Thank you so much. Last but not least, we have Andrea.
All right. Andrea also sent a couple of